Unfortunately, I have to miss the session due to your commitments. Any of you present at the session may present, but I cannot present anything if I didn't see it. So, Alex, you are before time, half a minute. Oh no, even you were 5 minutes here ago.
I mean, I am supposed to begin? Or?
Yes, in a moment. But you wrote that.
But then I want to share screen.
I think you should just click sharing screen.
Well, I'm trying to.
Oh, yes.
Do you see my screen now?
Yes, we see the screen, we see you.
Okay, good.
Okay, I think it is time or still half a minute, I don't know. I think it is time. Okay, so we have problem session. And with some people I communicated and we communicated before, inviting people who didn't let us know they want to speak. They, of course, still can speak, present something. There will be hopefully time for this. We have the whole night for this. But let's start with maybe first Alex Eremenko.
Okay, do you hear me?
Yes.
Okay, so I want to recall about two outstanding unsolved problems, which probably many of you know them, but still I want to recall. So they are both about completely invariant planes, and they involve some complicated topology. So the first one is very old. It is called Makian conjecture. Actually, I gave it this name. The story is shortly the following. Makienko had this statement in his thesis, and I was a referee, and the proof was wrong. So then I tried to prove it myself, and then failed and started to popularize this problem under the name Makienko conjecture. There is at least one published wrong proof, not by Makienko, by Manet and Rocha. So the conjecture is very simple. Consider a rational function, and suppose that you have a component of the set of normality whose boundary coincides with the Julius. In some modern terminology, this means that there are no buried points when the Julius set is the union of boundaries of components. But let's look at just one component and suppose that its boundary coincides with the Julius set. Then it is conjectured that D must be completely invariant. So, well, if you think a little about it, it looks almost evident. Think of what a possible counterexample will be. So suppose that D is an invariant domain, but not completely invariant, then F restricted to D is a ramified covering, so it has a degree. And it is easy to see that if degree of this covering is equal to the total degree of f, then it is completely invariant, and otherwise it is not. So any counterexample will involve continuous ramified covering of a simply connected region. Let's say simply connected for simplicity, whose degree in D is m, and on the boundary it is strictly big, which means that every boundary point has more image than the number of images in D. So it is not even clear whether such thing is possible for continuous maps, not speaking of rational maps. But speaking of rational maps, it is not even known that such picture is impossible for this.
I'm sorry.
So the simplest question related here is, can you have a z square plus c with a Ziegel disk whose boundary coincides with the Julia? We don't know. There was a question?
Yes, I have a question. When you say that f goes from c to c, not from c close to c close, do you mean that it's a polynomial?
No. I mean, I just forgot the bar.
Then well, I don't understand. If you take the map,
no, I mean rational function.
Okay.
I mean rational
if
function.
You have the rational function 1 over z squared.
Sorry?
The Julia set is the circle, and the map takes inside of the circle to the outside. Of the
I mean 1 over z square. Okay. I have to say completely invariant for the second. I have to say that. Okay. Completely invariant for some interval. That's the correct statement. Okay. Now I know one published paper on the subject. It is in the reference list below. So J must be an indecomposable continuum if we have a counterexample. And this is a separate question. Can the Julia set of a rational function be an indecomposable continuum? I recall what indecomposable continuum is. It's a continuum which is not a union of any two proper subcontinuums. A nice picture is in Kuratovsky's book, but this is some paradoxical thing, which is even more complicated than Vadala's. And I think Fatou himself asked whether the Julia set of a rational function can have Vadala's. Okay, so this is wide open. There are no substantial results.
Let me comment. Many years ago, I asked Manier the question whether it can be a fixed or periodic orbit in the boundary of Ziegel disk.
Yeah, so Manier
gave me immediately an answer which was wrong, and then after some time he admitted there are troubles.
Yeah, Manier had one published paper where this is considered evident, but with no proof. I tried to convince him that this is not correct while the paper was still circulating as a paper. But it was published too soon. I didn't have time to convince him. Okay, and the second question is a kind of connected with a somewhat scandalous story. So for a long time, this was considered as settled, and now it was discovered that it is not. So how many completely invariant domains can the entire function have? I recall that a rational function can have at most two. So in 1970s, Baker published, in 1970 exactly, Baker published a short paper, very short paper, with a very short proof that entire function, transcendental entire function, can have at most one completely invariant domain. So this was considered as one of the three main classical results of Baker in the theory of entire function. And unfortunately, it was eventually discovered that his proof was wrong. So what he essentially claims to prove in his proof is that if you have two simply connected disjoint domains and the transcendental function, then the pre-image of both domains cannot be connected. You cannot have both domains having connected. And surprisingly, this is wrong. And you don't even need a complicated counterexample. This is wrong for e to the z plus z. But domains are terribly complicated. And this is a recent counterexample by Rempe and Six-Smith, which is the counterexample to Baker's proof. So the question is wide open. The corresponding question for meromorphic functions, which is also open, well, one can sort of conjecture that there is at most one completely invariant domain for transcendental entire functions and at most two for transcendental meromorphic functions. So both results are known for class S, the Speiser class. These are entire meromorphic functions with finitely many singular values. So for meromorphic functions of class S, this was proved by Baker, Kotus, and Guignan. And for at that time, the theorem of Baker was considered as known and correct. And for entire functions of class S, this is in the same paper of Rempe and Six-Smith. So here is references. So these are two problems I wanted to report. I'm finished.
Yeah, so yeah, I'm just rewriting this. Some questions, solutions.
Well, maybe one comment on this. I think the conjecture is even stronger, not only that there is at most one completely invariant domain, but if there is one, then it should be the whole Fatou set. Yeah?
Yes.
Yeah.
Well,
and same for meromorphic functions. If there are two completely invariant domains,
if I'm not mistaken, this is also known for class S.
Yes.
Okay, some more questions. If somebody has a question, should I see a hand? No. Okay, so no more questions to Alex. Is Gennady Levin around at computer?
Do you want me to send this file?
Oh yes, please.
After I correct the mistake, huh?
Yeah, yes, please, yes.
Okay.
Right.
Yeah.
Okay, so how?
Oh, Gena is here. Great.
How do I stop sharing? Stop sharing. Okay.
Okay. Gena, your turn. Do you have a file or you want to?
No, I
You want
not
to?
very well prepared, so
I don't know techniques.
I will talk only.
Okay.
So when you asked to tell me something in the problem session, one question. I recalled question that came to my mind last year. And it is about topology of Hermann rings. Well, as far as I understand, almost nothing is known in general. So you can ask almost any question about this and it probably will be open. But my question was motivated by something. So the question, it has maybe two parts. So first, is it possible that that closures of two different Hermann rings intersect? This is the first question, the first part of this question. And the second part, again, can the complement to the closure of a Hermann ring be infinitely connected? So can it contain, for example, more than two components? So well, of course, if the boundary of Hermann rings Jordan curves, then the answer to both parts of this question is no. But since it's also not known whether maybe it's another conjecture, whether it's always the case that the boundary Jordan curves. But what I tell probably, well, it looks simpler. Okay, so it looks maybe simpler to just to say that it is not possible. So it is. So I was not sitting and looking for question about Hermann rings. Not just it. So if the answer to both parts is no, then union of closures of Hermann rings has nice functional analytic property that every function which is continuous on the union of closures and analytic inside is uniformly approximated by rational functions with poles outside. And then it gives a nice description of fixed points in some rather general situation of so-called Real-Thurston push forward operator, and which in turn implies some transversality results for rational functions with summable critical points in some spaces of nearby rational functions. So it's probably no point to explain in details. It's you can look at archive and it's in there. So that's okay. Of course, you can ask at least the second part of this question also for Ziegel disks, whether the complement to the closure of Ziegel disk can contain more than one component, infinitely many components. But I mean, Ziegel disks are not obstacles in this problem about this push forward operator. So that's why I stated only for Hermann rings. But the question exists also for Ziegel disk. No, of course, not polynomial Ziegel disk, because for polynomial, it's not possible by maximal principle that the complement to the closure contains for Ziegler disk contains more than one component. But for rational functions, I don't see any obstacles.
But do you have in mind in the composable boundary, or the boundary is...
Well, of course, that's first kind of, but it's not clear why, if it is even not if it is indecomposable, why still? I mean, it can be indecomposable, but the complement can contain only finitely many components. I don't think it's also very much related. I think maybe I'm wrong. There is a result by Adrian Cherita that there are holomorphic maps with proper Ziegler disk with an indecomposable boundary. But I think in this example, the complement still simply connects. That's it.
So, does somebody want to ask?
Solve.
Solve. No. Okay, I was told that Alexandre Desotti has something to tell. Is Alexandre with us?
Hello, hello. Yes.
Oh, yeah.
Okay. Yeah.
Did
So
you present something?
yeah, just a small
You
question.
are welcome. You are welcome.
You can hear me right?
We can hear, but we cannot see you.
Okay. I think it's fine. So yeah. So I had this question. I mean, so I don't know. It's probably a very simple question, but so when you look at Ziegler disk again for rational map, and so you look at the closure of the critical orbit, which is associated to this Ziegler disk. So in the case where the rotation number is high type, so we go like 3 different possibilities. So either the rotation number is Hermann, and then in that case the lambda, the closure of the forward orbit of the critical point, is going to be the boundary of the Ziegler disk is going to be a Jordan curve. In the case where the rotation number is Bruno but not Hermann, then lambda is what is called the one-sided Harry Jordan curve. So it's sort of counterboot K supported by Jordan curve, and in the non-Bruno in the non-Bruno case, so this is just a counterboot K. So with Yang Fei and Davut Charagi, so we proved that for high type and rotation number which is not Hermann, then the Hausdorff dimension of this set lambda is 2, and we have k's. So in that case, so we've got this one-sided Harry Jordan curve. So you can define endpoint the same way as you define endpoint for counterboot K. And so if you look at the dimension of the set of this set where you remove the endpoint, you can ask what is this? And so there are some cases you could prove that for some specific rotation numbers, the dimension will be 1, which means that we have a dimension paradox. So a dimension paradox, so it's when like we have like this kind of object made of curves whose total dimension is 2, but if you just remove the endpoint of these curves, you get an object of dimension 1. So this kind of phenomenon was discovered by Boguslava Karpinska for exponential maps. And so here the proof that the hair for the Ziegler disk dimension 1 is very similar to the exponential maps. And the way we make it work is because of the dynamic of the renormalization. So we choose the rotation numbers so that this looks very much like an exponential maps, and we can apply same arguments. So the question is, does this hold in general for, let's say, high type non-Hermann rotation number, that the paradox, dimension paradox, does it hold for this? Or is there a counterexample in simple family of rational or polynomial maps? Does the dimension depend on the combinatorics? Oh, so this is my question.
But these endpoints of the bouquet are not endpoints in the boundary of Siegel disk, but elsewhere, right?
Yes, so they're not on the boundary of the Siegel disk. They're only on the post-critical closure.
I'm asking because there is this problem whether connected Julia set for rational function, except exceptional cases, has Hausdorff dimension bigger than 1. For polynomials we know, but for rational functions we don't know. So if there is a basin of attraction, then already the boundary of the basin, except exceptional cases, has dimension bigger than 1. So the parabolic would be, I believe, similar, though more complicated. So the real problem is if there is a Siegel disk, and its preimages or Hermann ring. And then this theory you told about says that in many cases, Hausdorff dimension is even 2. But I would like to know, is it at least, is it more than 1 by maybe some other magical methods? I don't know.
Yeah.
This is my question, comment to your.
Well, thank you for the question comment.
No, yours is concrete, technical. Well-known problem, and your theory might help, but it is too complicated. I think there should be some easier way.
Yeah. So yeah, I'm not sure how to get about this, but maybe, I mean, there was the idea of using like this beta function that Neil Dobbs was talking about in his talk.
Okay, yeah.
But,
well, one can try to, well, sometimes boundary of Siegel disk has dimension bigger than 1.
yes,
But sometimes
but,
no, and one can prove it with the use of beta function. But it can be smooth, so then you.
Yeah. Yeah.
Some comments, questions related to this? No comments. Tushardas sent me 10 minutes ago some 3 pages of problems, but I'm not acquainted with them. So, and he is not here. He apologized that he cannot participate. Maybe we ask.
I can ask another question if there's
You are welcome.
thought.
You are welcome.
Okay. Right now?
Mm-hmm.
Okay, so the question is, do there exist degenerate Hermann rings? What do I exactly mean? Can we have a Jordan curve so that the restriction of our function on this Jordan curve is conjugate to irrational rotation, but this curve is not a subset of Siegel disk or Hermann. It is a subset of the Julia. Okay? So can we have such curve at all? can we have such curve smooth or analytic?
Say again, you asked about Jordan curve and Julia set.
Can we have a smooth curve,
In
Jordan curve,
Julia set.
so that the restriction of function on this curve is irrational rotation.
Ah, okay.
But this curve is not contained in Hermann ring or Ziegel disk.
Mm.
It is contained in the Julia set. Can we have a curve in the Julia set on which the function is conjugate to irrational rotation?
Mm.
So, analogous to Kramer point. So the non okay. So as Kramer point related to Ziegel disk, such curve would be related to Hermann. But it is not clear whether such thing can exist. Except the circle, of course.
Yeah.
So,
Well, at least I can make a comment on that at another occasion. Apparently, I assume that such things may exist, and sort of asked whether in the count of Ziegel disks, Hermann rings, and Kramer points in terms of critical points, whether somehow these such curves can also be included into this count, and if so, whether they would use 1 or 2 critical points. But of course, to ask whether they exist at all is a much more basic question.
some more questions?
Yeah, but Alex, you are asking for smooth curves, yeah?
Not necessarily. Even we
Okay.
don't know any.
Okay.
I'm mostly interested in smooth curves, but
Yeah.
say analytic curves.
Mm.
But we don't know any. I don't know any example.
Yeah, okay.
Except the circle.
So as a comment, I wasn't expecting to join the discussion, but for exponential map, we cannot. So if you have a smooth curve, anyway, if you have a smooth Jordan curve, it contains points, there are points on the curve whose orbits are dense.
Sorry, what curves do you have for exponential?
So if you have a, if you take, let's say just z goes to exponential of z as your function, as your map. If you take any smooth Jordan curve, its orbit will be dense.
So what? Whose orbit will be dense?
The orbit of the curve.
Yeah, but I'm talking about invariant curves.
So
it's not invariant.
I'm talking about invariant curves. When I say that f is conjugated to rotation, I mean the curve is invariant.
Yeah, and I'm saying that if the curve is smooth, it's not invariant in a strong way.
No, but if the curve is not invariant, then I don't understand what does it mean restriction is conjugated to something.
No, it's not.
It has no meaning then.
No, neither gives you, says you it is false. Expect.
I meant in my question, I meant invariant. Certainly. And I don't know such
Yeah, and
examples.
I'm just saying that
I don't know such
that
examples.
they don't exist in exponential dynamics.
No, they don't. I mean, they don't exist for entire functions.
Yeah.
This I think is true. If you have a smooth invariant curve for entire function, then it must be contained in the Ziegler or to be a circle. So this thing does not exist in polynomial or entire dynamics. It may only exist in rational or monomotor dynamics, like Hermann rings. That's why I call it degenerate Hermann.
So, who is next? So, shall we finish?
Maybe we can share the file that this person sent us. We can share it with other people.
I sent it to you
Okay.
just before the session. You can look at it. You can just show us, but I don't. It's not readable in a few minutes.
You mean Tushar's file?
Yes. If you
Where do you send it to?
have,
To
it is sent to you also. He sent it first to us, and I forwarded it to David, Leticia, and Artyom. Everything.
It's Anna speaking. So Anna, we didn't send it to you yet.
No?
We can share it now if you want. Do you want me to share it in the chat?
I don't know. No, Anna has it.
Okay.
Her first.
Okay.
Anna, me,
Okay.
Marius, and I forwarded it to you.
Okay.
Everything was 10 minutes before our session. So
I would be also interested in having the question by Alexander Dezotti being written down, because I didn't catch this question exactly. So may I ask Alexander to write down the question you asked?
Well, it is written. I will attach a file on it.
Okay, I meant another Alexander. Sorry, I know
you mean another Alexander?
I'm sorry, not you. Of course, I know your questions are written and very intriguing, but Alexander Dezotti also asked questions, and just in an oral way. Maybe he could write it down. Can you ask him? Is he still, Alexander, still there? I'm not sure.
He's still here. So our idea was to record this and then transcribe it or make a summary of it and put it in the website, perhaps after talking to the people that contributed to it, so that we have a summary or something like that. I don't know if Alexandra left.
Yeah, sure.
okay. Okay, so Anna, do you volunteer to show us what Tushar sent to us, or maybe it is too courageous to look at 3 pages of text without knowing it? Okay, so I think we finish. David, shall we finish? Leticia, shall we finish? Okay, so we finish and see you tomorrow.
See you.
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 Night.
Bye.